Um, okay, it's time to get it started. Hello, everyone, and welcome to our fourth week of CS 2100. Um, I hope you're all okay after last week's insane windstorm. Yeah, I've never seen anything like that in Utah. We had a bunch of trees fall around our house, and waking up and walking outside was kind of a crazy experience. But luckily, none of them landed on any of the houses. It was almost a miracle. Like the way they were falling was kind of in between houses towards the street, so we really got lucky. But still, no internet at home, so I'm actually in my office right now. Um, so I have a bunch of announcements in the beginning. I want to kind of discuss quiz one a little bit and how it went and what are some of the lessons we learned. Then I'll make a couple of announcements, and then we'll do a bunch of proofs together. So that's the plan for the next 50 minutes. Okay, so about quiz one. Well, it was bad timing, but weather is impossible to predict, so it is what it is. As you can imagine, lots of you had issues related to storm-caused power and internet outages and so on. And Bay and I really tried to accommodate all of you. And so there was a redo of the quiz on Thursday, and we extended the deadlines and so on. So I think all of you actually got a chance to submit it in the end. And another thing that we kind of agreed to do, despite what the rules and the syllabus says. Because of the situation this whole past week, we were also very lenient in terms of accepting late submissions and accepting submissions where students struggled submitting through Gradescope and they emailed us and so on. So there was probably dozens of exceptions like this that we kind of let slide. And that's all fine. It was a weird week. However, I really wanted to give you a heads up that this is going to change dramatically for quiz 2 and all other exams from now on. Definitely, there was this sense that despite all these power outages, there was quite a few students who have not really read the syllabus and instructions for quizzes and so on. And so for quiz 2, if you fail to submit your solution using Gradescope, so no emails, no messages, anything like that, and on time, you will get 0 points on quiz 2. And so we will not accept any kind of excuses such as internet outages or my internet failed for 2 minutes as I was submitting it and hence I didn't manage to submit and so on. We did increase the grace period from 50 minutes to half an hour. So that really gives you a lot of time to actually submit your quiz and use this time wisely. If internet is flaky at home, have a backup plan in place. Like half an hour is enough to, walk to your neighbor's house or even drive somewhere. So make sure to put things in place between now and quiz 2 so that you really manage to submit your quiz to Gradescope without any issues. In this case, if you do run into any outages in terms of power and internet, we will accept those as an excuse only if it's supported by a written letter from your power or internet company. So these things do happen sometimes. And if they do happen, you will have to request a letter from your power or internet company that you will submit to us. So again, I encourage you to read the syllabus and instructions ahead of time. Also, make sure you know how to submit your solution using Gradescope. Make sure you know how to scan your quiz as a PDF document and so on. Make sure that everything works on your end. There's still 2 weeks between now and quiz 2, and there's plenty of time to practice this. And if you run into any problems or technical issues, there's plenty of time to seek help during office hours from TAs or from us. So keep this in mind. I mean, we really will change how we do things for quiz 2, and we will be way less lenient. So make sure you get these things right. Okay, so we made a few announcements about this on Canvas. Make sure to go through them. So that's kind of about quiz 1 and the upcoming exams. A couple of quick announcements. So homework 1 scores are out. Homework 2 is due this Friday, September 18th at 11:59 p.m. Don't forget about that. Quiz 2 will be in 2 weeks, and it'll be all about proofs. So the material that will be in quiz 2 are proofs, and that's it. Know that students typically find this quiz to be the hardest one. So make sure to prepare accordingly. And related to that, let me just repeat once more. If you feel that you're struggling in 2100, there is a couple of different ways to seek help. You can always ask questions on Piazza. Piazza has been quite active, which is great to see. And we keep an eye on it and try to respond promptly to all of your questions. You can also come to TA office hours. There are a number of available slots every week. And so between now and the homework deadline and quiz 2, there is plenty of opportunities to come to office hours and discuss any issues or problems or misunderstandings you might have with us or TAs. On top of office hours, or in addition to office hours, the department also has a tutoring center that includes CS2100. And we made a recent announcement about that on Canvas. So that's yet another resource that you have at your disposal to seek help for 2100. So read the announcements, and you can come to the tutoring center as well. Finally, I mean, I already mentioned this a couple of times. I think for many of you, it might be a good idea to bootstrap or create a virtual study group where you can, discuss problems with your peers and so on. I think for me, that was always a good way to study. However, be careful about our cheating policy. So don't, copy solutions from each other. That's what we don't allow. So those are the announcements I have. We have a TA monitor, Lynn, our chat, and raised hands and so on. So if you have any questions at this point, please let me know. Okay, so if there are no questions, let's do a couple of proofs together. And for at least one of them, we'll do breakout rooms as well, because I think that's a nice way to, talk to your colleagues and try to work on problems together. Okay, so here's the first one. So it's a direct proof. It's a little practice of division theorem. So let's see how we would go about proving this. So first, as a quick reminder, what is this symbol? This symbol means divides. So we want to prove that if 9 divides 10 to the power n minus 1 minus 1, then 9 also divides 10 to the power of n minus 1. And we want to use direct proof to do this. So, okay, so what do we know? So we know that from division theorem that 10 to the power of n minus 1 is equal to 9 times some k, where k is an element of z. So that follows from division theorem. And now from here, you should keep your goal in mind, right? We want to prove something about 10 to the power of n minus 1. which means we want to somehow transform this expression 10 to the power of n minus 1 minus 1 into 10 to the power of n minus 1. So how do we go about this? Well, the hardest part is probably to deal with exponents. So how do we get to 10 to the power of n minus 1 to 10 to the power of n? Well, we have to multiply it by 10. And given this is an equality, to preserve this equality, we have to multiply both sides by 10. So let's do this. So let's multiply both sides of this equality by 10. Now on the left-hand side, we get 10 times 10 to the power of n minus 1 minus 1 is equal to 9 times k times 10. Okay, so let's multiply this out. So we get 10 to the power of n minus 10 is equal to 9 times k times 10. Okay, so we are getting closer. So what we have on the left-hand side is 10 to the power of n minus 1 minus 9 is equal to 9 times k times 10. So then we get 10 to the power of n minus 1. Great. We have our goal is equal to 9 times k times 10 plus 9. And that is equal to 9 times 10 k plus 1. And that is now equal to 9 times some L, where L is an element of Z. And that follows from closure of plus and multiplication. Okay, so we got that 10 to the power of n minus 1 is equal to 9 times L, which means that 9 divides 10 to the power of n minus 1. And this proves this proposition. Okay, so I'll take any questions you might have now. Let me look at the chat. Okay, well, all the questions got resolved by your colleagues. So thanks a lot for jumping in. Okay, so I have another slightly simpler proof that also uses the division theorem. And I'll give you a couple of minutes to try to solve it on your own first. It's a little bit easier, I think, to derive the proof. So why don't you try to do it on your own, and then I'll solve it for you guys. I'll give you maybe 3-4 minutes for this.
Professor, there is a question from the chat.
So there is a great question from Nathan. So, you know, you'll be given a lot of tools on how to solve, on how to do proofs, you know, like induction, contrapositive, direct proof, and so on. The question is, how do we tell which one we should use? And if it isn't specified, can we use whatever method we'd like? So let me first answer the second question. So in this course, we will basically always give you a hint for which method to use. And you know, if there is no hint, that means that you should use direct proof. And if it's some other type of proof, we'll give you a hint. And so why do we do this? Well, because this is basically an intro to proofs course. And in fact, one of the hardest parts of proving a proposition is actually figuring out which method to use to prove it. because the hardness of the proof often highly depends on which method you use. And so, we don't want that you start with the method that wouldn't lead to an easy proof, and then you get stuck, and then you have to retrace your steps and so on. So that's why we always give you a hint what to use, and we suggest that you stick to this hint because it's typically the easiest way to prove the given proposition. But in practice, right, if you are doing these proofs for real, you would have to figure out which method to use on your own, and that's where actually lots of ingenuity comes into play. That's kind of the hard part. Okay. So I hope you gave this one a try. Like I said, I don't think it's too hard. Once you write down your facts, it's pretty easy to derive this right-hand side. But so let's see how we would go about this. So we know that A divides B. That means that B is equal to A times some K, where K is an element of Z. Then A also divides C. So that means that C is equal to A times some L, where L is an element of Z. Let me just point out that a common mistake that people make here is that they would use the same letter to express both B and C in terms of A. So if you wrote that C is equal to A times K, and you reuse the symbol, that would lead to a wrong proof, because B and C are not necessarily the same. So be careful when you're introducing new symbols. Okay, and from this, we want to prove something about B times C. So let's see what is B times C. B times C is equal to A times K times A times L. And that's equal to A squared times K times L. And that's equal to A squared times M, where M is an element of Z. And this is because of closure of multiplication under integers. And that's it. That finishes our proof. So we showed that B times C is equal to A squared times M, which means that A squared divides B times C. And that's it. Any questions about this proof? Okay. So maybe just to kind of put things in perspective. So I would consider this to be, let's say, a very easy quiz question. You should be able to solve a proof like this in just a couple of minutes. Okay. All right, let's move along. Let's now switch types of proofs a little bit and do one proof by contradiction. So we want to prove using proof by contradiction that if A is a rational number and B is an irrational number, then A plus B is irrational. Okay, let me just remind you about how proof by contradiction works. So if we have a proposition, P implies Q, that's the typical form of our propositions. Then in proof by contradiction, we assume P and not Q. So we state P and not Q as facts. And this is basically saying there exists a counterexample to this proposition. And if from here we manage to derive a contradiction, that means that a counterexample cannot exist, and hence your original proposition holds. Okay, so in proof by contradiction, I think it really helps that you first identify what P and Q are, so that you can actually write down P and not Q. So in our case, in case of this problem, P is this whole thing. A is a rational number and B is an irrational number. So that's P. And then A plus B is irrational, that's Q. So what is P and not Q? So P and not Q is A is rational, B is irrational, so that's B, and then we need not Q. So not Q is A plus B is rational. Okay, so this is P and not Q. Now from these facts, we have to derive a contradiction. And again, you need some intuition here, and that's why I keep stressing out, like, to practice for quiz 2, you should really solve a lot of different kinds of proofs, because then, you know, you will have a good sense for basically how to proceed, how to do them, like what the next step should be. Now, if I look at this, I can't really write much about this fact that B is irrational. We don't really know how to express B in this case. However, we do know how to express rational numbers. And so we'll use that to handle the other two facts. So if A is rational, that means that A is equal to, let's say, K over L, where K and L are elements of Z. And then if A plus B is rational, that means that A plus B is equal to, let's say, M over N, where M and N are elements of Z. Okay. Okay, now what would lead to a contradiction? Well, we don't know much about B. So let's try to derive what B is. And maybe that will lead to a contradiction. So B is equal to M over N minus A. And that is equal to, let's plug in A in here, M over N minus K over L. And that is equal to, let's do a little bit of algebra. We have N times L below, and above we have M times L minus K times N. Okay, and all of these are integers, and so that is equal to, we can do substitution. Let me do like X over Y. Because of closure, of subtraction and multiplication. So we have B is equal to X over Y, where X and Y are integers. So that means that B is rational. And that contradicts our assumption that B is irrational. So we have a contradiction between this here fact, B is rational and B is irrational. And hence no counterexamples are possible. And this concludes our proof by contradiction.
There's a question.
Okay, any questions about this?
Oh, yes, from the chat. Do we need to specify next to y to be not 0? Because B is...
Great question from Justin.
Yeah.
Do we have to specify that in A is equal to K over L can be 0? That's a great one because, yes, you do have to specify this. And it slipped my mind, so thank you, Justin, for reminding me. So here, L cannot be 0. And here, N cannot be 0. And here, Y cannot be 0. And we know this because neither N or L are 0. So that's a great point, Justin. Thanks for reminding me about this. Any other questions about this proof? So let me see a little bit about how we're doing with time. Okay, there's plenty of time. So let's do a couple of more proofs. Let's actually, I did this induction problem in lectures and in the previous recitation section. So in this one, let's do the other one that I have. So let's do this one. So we want to use mathematical induction to prove that for all integers greater than or equal to 0, 10 to the power of n minus 1 is divisible by 9. So that's a little bit related to our first problem that we proved in this recitation. So, so I'll create breakout rooms so you guys can discuss the structure of this proof and how you would go about it. But just as a quick reminder about induction, right? So first you have to write down what your predicate that you're proving is. So your Pn. Then you have to show that it holds for your base case. So you have to see what your n is. Does it start with 0 or 1 and so on? And then you have to prove your base case. Then you have to write down your inductive hypothesis. I like to express inductive hypothesis in terms of n. And then in my inductive step, I prove the predicate for n plus 1. But it's equally fine to start with n minus 1 and prove it for n. And so let's do breakout rooms now, and you guys can give this proof a try, and then we'll do it together. Okay, you'll need to, I think, click to join the room. And so let's resume in maybe 5-6 minutes and do this proof together. Okay, welcome back, everyone. So I hope this was fun and useful, and I hope you managed to solve this one. So I would say that's I would say on an easier end in terms of proofs by induction. Okay, so let me try to do this for you guys. Okay, so first we want to write down the predicate we're proving. So P of n is equivalent to 9 divides 10 to the power of n minus 1 for n greater than equal to 0. Okay, so that's our predicate. Let's first do our base case. Never forget your base case when doing proofs by induction. So in this case, our base case is when n is equal to 0. And be careful about this. Sometimes we start with 1, sometimes with 0, and so on. So we want to prove P of 0. And so we want to show that 9 divides 10 to the power of 0 minus 1. And so we have 9 9 divides 0, and that holds because 0 is equal to 9 times 0, as a reminder. So this proves our base case. Now we have to write down our inductive hypothesis. And I'm going to assume that P of n holds, which is equivalent to 9 divides 10 to the power of n minus 1. Okay, and now we do our inductive step. Where we want to show that P of n plus 1 holds. And we probably want to use the hypothesis to show this. So again, I already mentioned this. I kind of like writing down my hypothesis in terms of n, and then in my inductive steps showing that P of n plus 1 holds. Somehow I find it more natural, a bit easier maybe. It's totally perfectly fine to express your inductive hypothesis in terms of n minus 1 and then prove that P of n holds. So both are totally correct, totally fine. It's just a matter of personal preference, and I find this one usually a bit easier. Okay, so what do we want to show? We want to show that 9 divides 10 to the power of n plus 1 minus 1. Okay, so how do we do this? So let's start with 10 to the power of n plus 1. And we want to somehow plug in the inductive hypothesis, right? So let's see how we go about this. So that's equal to 10 times 10 to the power of n minus 1 and that is equal to so similarly, this is kind of similar to the first proof we did, right? Keep in mind that we want to plug in inductive hypothesis. So we want to use it somehow, which means that we probably want to get this expression on the right in the inductive hypothesis somewhere down here, so that we can then plug in that 10 to the power of n minus 1 is equal to 9 times some k, where k is an element of z. So I'm trying to get this expression 10 to the power of n minus 1 down below so that I can plug in a hypothesis. So I have 10 to the power of n, but I'm still not quite there. So how do I get there? I do something like this. 10 to the power of 10 times 10 to the power of n minus 10 plus 9. So that's equivalent, right? And that is equal to, I pull out 10 times, what do I have? 10 to the power of n minus 1 plus 9. Great. So at this point, we can plug in the hypothesis. So we get 10 times 9 times k plus 9. And that's equal to, we pull out 9 times 10k plus 1. And now we do our usual substitution. So that's equal to 9 times some L because of closure of plus and multiplication. And L is an element of Z. Okay, so we showed that 10 to the power of n plus 1 minus 1 is equal to 9 times L, which means that 9 divides 10 to the power of n plus 1 minus 1. And so this concludes the proof. Okay. I know that proofs by induction are kind of tricky. And it takes some time to wrap your head around them. So, so try to practice them a lot at home. Any questions about this proof? Okay. Okay, I really hope that no questions is a signal that you all guys, you all got it, as opposed to the opposite, that you have no clue what the heck is happening, and so you don't even know what questions to ask. But yeah, don't be shy to ask questions. I mean, you can always write them in the chat and so on if that's what you prefer. Okay, great. Let's maybe at least start one more proof. We have 5 minutes left. So the one I wanted to do, let me try to close this. It's funny. Sorry about this. I'm stupid enough that I don't know how to. Okay. I didn't know how to move my Zoom toolbar. Okay. So we want to prove that the square of an integer not divisible by 5 leaves a remainder of 1 or 4 when divided by 5. And our hint here is that you should use proof by cases. So this is the kind of hint you would get in the quiz. So we would just say use proof by cases. Here I'm giving you a little bit more of a hint, where each case corresponds to the possible remainder for the integer when it is divided by 5. So one thing I want to mention is that unless we want you to prove some proposition using a direct proof, we will always give you a hint what kind of proof strategy you should use. Of course, in real world, when people prove these big theorems, I mean, nobody gives them a hint because they're doing it for the first time. And lots of ingenuity in terms of proving something comes actually from figuring out which strategy to use, because some strategies will lead to much more complicated proofs than others. Given that you are just starting with doing proofs and so on, we'll always provide you with hints which strategy to use. So you don't have to worry about it. Okay, so here we want to use proof by cases. So how many cases we're going to have? Well, we have to consider integers that are not divisible by 5. So that means integers whose remainder when divided by 5 is either 1, 2, 3, or 4. So our case 1 is going to be integer that is not divisible by 5 when the remainder is 1. So our n in this case, in case 1, is going to be 5 times k plus 1, where k is an element of z. Let me just write down also case 2. I won't probably have time to do all 4, so you guys can try the other 2 at home. So case 2 is going to be n is equal to 5 times k plus 2, where k is an element of z. Note that here it's fine to reuse k. It's fine to reuse the same symbol because these two cases are completely independent. You're proving them completely independently. Okay, so let's do the first one. N is equal to 5 times k plus 1. Want to prove something about the square of this integer. So n squared is then equal to 5 times k plus 1 squared. And that's equal to 25k squared plus 10k plus 1. And we have to show that a remainder of this square when divided by 5 is either 1 or 4. So we already kind of have this 1 in the end. So let's try to work with that. So we get that's equal to 5 times 5k squared plus 2k plus 1. And that is equal to, we can do our substitution now, 5 times L plus 1. And this where L is an element of integers. And we can do this because of closure. Closure of integers under plus and multiplication. Okay, so this proves our case 1, right? We got that this square gives a remainder of 1 when you divide it by 5. So I actually have to stop now because Bay will have to start the next recitation soon. Any questions about this proof? Other 3 cases are very similar to case 1, so please do them at home. It should be fairly easy. So let me look up the chat. Right, yes. So there is a question about the missing cases. Right, so there'll be 4 cases. So I wrote case 1, case 2 here. There'll be also case 3, which is n is equal to 5 times k plus 3. And there'll be case 4, where n is equal to 5 times k plus 4. Any other questions? Okay. So thank you all for joining. I'll see you next Tuesday. And make sure to practice proofs. And don't forget about the homework too. Thank you all.